So if I have this series of my function f of x equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial, etc., as we keep going to x to the n over n factorial for any n, I want to know eventually what is this series representing, what function. So let's do some math work with this. What if I derived this function? So I would take f prime of x. Derivative of 1 is just 0. Derivative of x is just 1. X squared over 2 factorial, well, we have 2 times x to the first power now. Underneath, that's just a constant 2 factorial, which is just, well, 2 factorial is just 2, and that ends up canceling out. So this little part here ends up just being x plus 3x squared over 3 factorial being 3 times 2 times 1. Well, the 3's just cancel out, and we're left with x squared over 2 factorial. With the next one here, we have x to the fourth. Derivative of x to the fourth will be 4x to the third over 4 factorial. But then again, 4 factorial is 4 times 3 times 2 times 1. Well, the 4's just cancel out, and we really just have x to the third over 3 factorial plus, and then the same thing's going to happen over here to the right. We'll have bring down the n times x to the n minus 1 over n factorial. We kind of cancel out the n and the n factorial like we did over here, and we can rewrite that to be x to the n minus 1 over, well, n minus 1 factorial plus, etc. And we keep going. So this new f prime series is really, we can get rid of the 0, so we just have 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the n minus 1 over n minus 1 factorial. And we notice we get the same series we basically started with. If I did the next power, it's really just x to the n over n factorial. Okay, so our derivative of our function, our series, is itself over and over again. Now might be something we want to think about later. So let me just find, for right now on the side, f of 0. We plug 0 into our original equation up here, and, well, 1 comes in plus 0 squared over 2 factorial. And we can see that this really just becomes 1 plus 0 plus 0 plus 0, which is just 1. And so f of 0 is just 1. Alright, so let's go back to thinking about what function do we know, what function do we know that when we take the derivative of that function, we get itself no matter how many times we do it. Since we have this f prime is equal to f of x, well, what function do we know that maybe has the same thing occurring? And a function that really just comes to mind here is e to the x. Because f prime of x is still just equal to e to the x. So to recap here, f prime of x we said was equal to our f of x, and the only function we know that to be true for right now is just e to the x. So maybe this series here is that function e to the x. Okay. Well, let's set y equal to f of x. Okay, it was right in terms of y, different rate of notation here. And so we said the derivative of f of x equals the original function f of x. In terms of y, dy dx equals y. Okay, and so now I can solve maybe this differential equation. I'm left with dy over y equals dx. Okay, let me integrate this on both sides, and now I have the natural log of y equals x plus c. Now let me solve for y here. I can take both to the e power, and I'm left with y equals, all right, e to the x plus c, okay? And then with our rules, we've done in algebra, not algebra, in calculus, calc 1, we know this ends up just being y equals k e to the x, k being a different constant. Well, we're given the value, we found previously that f of 0 equals 1, so I can apply that to my little equation here, okay? So when f of 0, when x equals 0, my y equals 1, so we plug that in, y equals k e to the 0 power, and we just get a k value now of 1, and so our equation here, y is just equal to e to the x, with a k of 1 that's up front, but that's imaginary there. Okay. Well, if we graph the partial sums of this equation, where does it seem to to be converging, to be similar? I would assume, just from our graphs, you look at your calculator, between -1 and 1, it kind of looks like it's converging. That's a popular interval that's used a lot. If you just graph the first couple partial sums here, but it might be greater than -1 and 1. As we keep adding more and more partial sums, it seems like that convergence might occur past this interval. And actually, in the real answer, the final answer, is that this interval convergence will work for all real numbers. Okay? And so our convergence, our interval of convergence, we can't see on the screen here, our interval of convergence, our interval of convergence is over just all real numbers. And as we complete this series infinitely many times, it will end up being converging over the whole equation, y equals e to the x. Hope that explained it a little bit. Have a good day.